easy? Hard? Okay, yeah. It seems like the class may have voted that this one is the one that's making people a bit nervous. But you guys are going to totally be on top of things for milestone 3 and 4. So you're thinking long term. It's great. Okay, so we're talking about path search algorithms, and we got to Dijkstra's algorithm at the end of last lecture. Dijkstra's algorithm is a very good algorithm. It's very efficient. Oh, is it not working? Or? Thank you.
Is that working now? Okay, so at the end of last class, we got to Dijkstra's algorithm. I'll turn this down a little bit. It's a little bit booming. Which is a good and efficient path search algorithm. But we saw we waste some time exploring in directions that are kind of going away from our destinations. They're unlikely to lead to anything very good. So maybe we can do even better. And you can do better. And the class of algorithms that can do better than Dijkstra's are called astar algorithms. They're pretty small code changes, so it's not a lot of different code. If you implement, my advice for this milestone is actually implement Dijkstra's algorithm, get it working, and then try to make an astar algorithm work. An astar algorithm is not much additional code, right? It's just a bit of thinking, make sure you get it right. Okay, so what are astar algorithms? Well, they're enhancements to Dijkstra's algorithm. They build on top of it. They use what are called domain-specific heuristics. So a domain-specific heuristic means I know something about the graph I'm working with. If you don't know anything about the graph you're working with, you can't use an astar algorithm. They basically, I'm going to show you in a minute, but they use predictions about what's going to happen. So we know that we're working in a city map, and that means that we can actually estimate quite quickly which graph nodes are closer to our destination and which ones are further. Okay, so if this was a graph that had no meaning, it was a graph of maybe social network or something, we might not be able to figure out if we're getting closer to our destination or not, but in a city map we can, because we actually know where all of our nodes are. They have a latitude and longitude point that we can turn into an XY point on the surface of the Earth, and we can tell if we're going in the right direction. So we're going to use that information that we understand this graph. The way astar algorithms work is they incorporate this information about am I getting closer or further from my destination into the wavefront ordering. Okay, so they use it as part of their sorting of which of these nodes in my graph are more promising than others. So they use the wavefront with just a different sorting function to order the most promising solutions first. And that's sometimes called best first search, okay? Because Dijkstra's algorithm is actually an enhancement on breadth first search. astar is an enhancement on that, and it basically looks at the most promising partial solutions, the most promising nodes in your wavefront first. Does that make sense? Everybody with me? Okay. And the reason that we're doing it this way, we kind of looked at a simpler approach at the end of last class where we just threw away things that were going in the wrong direction, and we saw sometimes that's too harsh, right? Sometimes you actually do have to backtrack or go in the wrong direction. So just what's called pruning, where you say, we'll not look at this node if it's going in the wrong direction, is too harsh, can make you get no solutions sometimes or get inferior solutions sometimes. Okay, so what does astar search do? So it doesn't prune, it will look eventually at the whole graph if it has to, but basically we're sorting our wavefront so that instead of searching outwards in circles, that's what we did with Dijkstra's algorithm, we're kind of searching outward in ovals. We're looking at the most promising solutions first, so these ones are the most promising. We've gone a fair distance from the destination, so we've built up a fair amount of travel time, but we can estimate that we've got a fair distance from the source, so we've built up a fair amount of travel time. And in Dijkstra's algorithm, we just sort by travel time, so we'd have this kind of circular wavefront. But with astar, we know these ones are closer to the destination, so they're preferable, so we prioritize looking at what they can reach first, and therefore our wavefront tends to grow towards the destination. Okay, so it kind of goes outwards in ovals, and we look at less of the graph in order to find the destination, which makes our algorithm faster. But notice we still are doing some exploration in the other direction. What that means is if there was a lot of blockages here, these were not good solutions, we will keep exploring this way, and we'll eventually go all the way around them. Okay, so it'll still, if it has to explore the whole graph, it won't prune anything, it'll find the best answer. Does that make sense? Okay, so how do we do that? So an astar algorithm is all about sorting your wavefront differently. And the key to sorting your wavefront differently is you employ something called a heuristic. So the heuristic is a guess of essentially am I getting closer to my destination or not? And we can compute this guess efficiently because we know we're in a city map. So we actually know where all our nodes are and which ones are getting closer to the destination. Okay, so I've drawn out a little piece of a city map here. So we're starting at the source. We've already done some exploration. So I've already found all these nodes, and I've pulled them off the wavefront, and I'm marking them red to show I've basically found the best travel time to them already. I've stored that best travel time, so I know I've visited these nodes, and I'm not going to do anything with them unless I find a better travel path to them. So these ones are all basically done. On my wavefront are the blue nodes. Okay, so these two blue ones, I put them on the wavefront because I got to this node and this node, and I looked at what they could reach. So I put them on the wavefront, and with Dijkstra's algorithm, I would sort the wavefront just by the travel time so far, which I'm calling best time, the best time to this node. Okay, so I've got two nodes I'm interested in right now, N2 and N1. And N2 has a best time of 45 seconds, so it's taken me a bit longer to get here. And N1 has a best time of 30 seconds, so I found a shorter path to it. Okay, so less time so far. So so here's a quick skill testing question. With Dijkstra's algorithm, like these blue nodes are the only two nodes of my wavefront. Okay, so here's my wavefront down here. Which of those two nodes would I take off the wavefront next in Dijkstra's algorithm? And this is not a hard question. I don't want to mentally tax you right before a midterm. So yeah, go ahead. What do you think? Right, so the first one, I would take N1 off because N1 has the lower travel time, so best time, like the known time to get to it. So that's what Dijkstra's algorithm would do. But N2 looks like it's closer to the destination. Okay, so maybe that is actually a more efficient way to search. So with an astar algorithm, we're trying to make that visible to the algorithm. Okay, so N1, let's write this down. So right now we have N1 on our wavefront, we have N2 on our wavefront. N1 has a travel time of 30 seconds, N2 has a travel time of 45 seconds. Okay, so this is like what I'm calling best time. It's like the known for sure time I took to get to this node. And if I sort by that, I'm just going to get Dijkstra's algorithm. Okay, so in astar, we're trying to sort differently. Okay, so I'm going to give you, let's see, actually maybe I'll just give you, I'll give you 1 minute to think about this. What kind of heuristic would you use? So something you can compute quickly, but that is, you're going to bring into your wavefront sorting so that you understand that N2 is looking closer to the destination. It's only 1 kilometer away, whereas N1 is 1.5 kilometers away. So can you think of a way to sort the wavefront where N2 is more likely to be looked at sooner? So I'm going to give you a minute to think about that. And then we'll call on you. So. Okay, anybody want to take a crack at this? What would you put in this, how would you sort the wavefront differently? Okay, so I'm going to go to, what's your number actually? C06? Somebody wanted to go incognito, they ripped off your label. I'm going to just turn on I think your volume's off. Go ahead now.
So the first thing I would do is I would calculate the distance between the current node and the destination node.
Okay.
And whichever one is closer gets put on top of the priority queue.
Okay, so you're basically saying you know the distance. How are you going to get that distance? Can you calculate that quickly? Because one of the things with these graph search algorithms, we're trying to look at fewer nodes. That'll make us faster. But we also don't want to do too much work per node. So how are you going to calculate that distance?
Is there the function from M1?
Yeah, so you have a fine distance between 2 points. So basically, you're going to use the distance as the crow flies, right? It might not be the real distance. Like it'll be an underestimate typically, right? Like the roads might not go exactly in the right direction, but you can guarantee, if I could fly from N2 to the destination and that took a kilometer, there's no way I'm going to find some roads that take less than a kilometer. So you're saying just compute that distance as the crow flies. You can do that really fast. That's right. And you're saying you're going to use that as your sorting function. So you're going to say, okay, let's not sort on this best time. Let's sort on distance to dest, in which case N2 is actually going to wind up at the top and N1 at the bottom of my priority queue. Because basically N2 has 1 kilometer and N1 is 1.5 kilometers. Is that correct? Yes. So it's a reasonable answer. One thing I'll note here, though, is that you don't have any preference based on, like if I had 2 nodes here that were right beside each other, they're both 1 kilometer away, and let's say this one I spent 50 seconds to get to. You don't actually have any way to tell them apart right now. You would consider both those things to be equally promising. Does that concern you? Okay, so that concerns you. So what would you do? Let me put you back on the line. What would you do to kind of address that concern?
Maybe I'd have some sort of range where if they're in this distance, I would then check the travel time instead.
Yeah, so you kind of want to combine the distance to the target and how much time have I taken to get here. Now, and put that into some kind of sorting function. Now, and that's the right idea. Now, one challenge you have is it's difficult to sort when you got different units. Right now we have seconds of how much time it took me to get here, right? This best time, that's my known time to this point. And I have meters or kilometers in distance to the destination. Difficult to sort on that because I got 2 numbers with different units. Does that give you an idea what you might do?
Maybe combine the units together and then you could have some sort of one variable to maintain.
So you say put them together and hash them into one variable. Yeah. Is that right? See, the thing is I need to use them as a sorting function though. So I could hash them and it'll turn into one number, but that number is like a random bucket of bits now, right? Hash functions, that's what they do, is they just, given a bunch of inputs, they produce like a bucket of sort of random string of bits. It's not truly random, but the idea is it actually looks pretty random. So, but this is the right idea. How can I combine these 2 numbers into one number? But I want to combine them into one number that I can sort on and that makes sense to sort on. Yeah, what do you think?
Can you multiply the numbers?
You could multiply them, although that might get weird too. Like if I had like a 1 second travel time so far at a really big distance, multiplying them together might give like a small number, but that doesn't necessarily mean this is good. It just means I haven't gone very far from my source and I'm still far from my destination. So multiplying is the right idea, but doesn't quite do it. How could I get these things into the same units? My problem here is I've got travel time up to where I am, and I've got distance to where I want to get to. So the different units are causing me pain. What can I do to get rid of these different units? It's not too complicated. And remember, I don't need to be perfect. I'm just sorting the wavefront, so I'm sorting it by a guess of what would be a good order to visit these things in. It doesn't have to be a perfect order. Okay, I'm going to go to D08. Okay, so D08, what would you do?
Yeah, maybe have like a average speed around the city so that you can divide the distance by this number to get the time.
Right, okay, so you're saying let's sort on total time. And my total time is going to be one part that's easy. Like this best time is I know how long it took me to get here, so that's easy. I also know how far I am from the destination. I can compute that with that M1 function. That can be computed quickly. And you're saying take the average speed limit. And I could figure that out maybe in load map. So let's say my average speed limit was 50 kilometers per hour. And you're saying, okay, with that average speed limit, I could, let me think of this. Let's say the average speed limit is 60 kilometers per hour, because it makes the math easier, okay? I just realized I don't want to do a bunch of ratios without a calculator. So with 60 kilometers an hour, that means that this estimated time is 60 seconds. That's how long it would take me to drive 1 kilometer. Now, this isn't perfect, right? I use the average speed. Also, my roads really won't go on this diagonal probably, but it gives me a reasonable estimate. So if I did this, I basically would get, for N2, I would get a total time of 45 seconds plus 60 seconds, which is just 1 kilometer divided by 60 kilometers an hour. So that is going to be 105 seconds. And for N1, I would get 30 seconds. Okay, so this is my heap. For N1, I would get 30 seconds plus 1.5 kilometers, which is 90 seconds worth of travel time at 60 kilometers an hour, which would be 120 seconds. Okay, so with this sorting heuristic, I mean, it looks pretty good, right? Like it actually says that N2 is better than N1 because it's closer, but if N2 had a really high travel time so far, it would actually change its mind. It would say, let's go look at N1 because it took me so long to get here. So it seems to be doing, and if I had 2 nodes that are right beside each other, one with a different time than the other, it'll actually sort those properly too. So, sound good? Does this look like a good heuristic? So this is a pretty good heuristic. Seems logical. So yeah, so total time is a pretty good thing to sort by. But now let's walk through and just see if this is everything we wanted. Okay, so I'm using this average. I use the average speed limit, distance as the crow flies, and I get what is my total time. So let's go back here. The top of my priority queue is going to be this node N2. So I'm going to look at it. I'm going to update its best time. So I've marked it red to show that, okay, I've updated the best time to it. I look at what it can reach. Let's say it can only reach 1 node. Okay, it's got 1 street segment coming out. So it can reach node N3, this one. And let's say my estimate of speed limit was exactly right. Okay, 60 kilometers an hour turned out to be exactly what the street segment was, and it was going exactly the right direction, so it took me 30 seconds, and I went halfway to the destination. So now I've only got half a kilometer left. And so if I take this, if I look again at my priority queue, so I put this new node N3 in, okay, so N1 is still on there. It's on there with what I had before, 120 seconds. So total time of 120 seconds. This new node N3 is also going to go into my wavefront. And it's got 75 seconds plus half a kilometer divided by 60 kilometers an hour. That's 30. That's equal to 105 seconds. Okay, so N3 is the best thing on my wavefront. I'm going to look at it next. So I take it out of the wavefront. I mark it as red because I've updated its best time. I look at what it can reach, and it can reach my destination. Okay, turns out it's got a street segment right there. Same thing, street segment goes exactly the right direction. It's actually 60 kilometers an hour, so I predicted it perfectly. It takes 30 seconds to travel that, so I reached the destination in 105 seconds. And I saved a bunch of work, because I didn't go look at this node N1 or anything it could reach. So it all sounds good. Is everybody happy? Okay, so and in most cases, it will actually work out this way. You know, you'll find the best path, and you found it faster. But there is a problem. So let me show you. There's a problem that can occur. Okay, so I never looked at this I never took this N1 off the wavefront. Okay, and let's say N1, you know, was going in the wrong direction, but it turns out it got onto a 401 on-ramp, and this destination is just right on the edge of the 401. Okay, so I had to go 1.5 kilometers. But I could do the 1.5 kilometers at 100 kilometers an hour, and that actually only takes 54 seconds. So I predicted a higher number, right? Like I predicted I was going to be able to drive at 60 kilometers an hour, but it actually turns out from N1 I could drive at 100. So actually, from N1, if I'd ever looked at it, I'd find there's a street segment that's part of the 401, goes right to the destination, takes 54 seconds, so I would have got there in 96 seconds. So I didn't get the shortest path. Our optimality tests for milestone 3 of tests of are your paths short enough are going to say it's not fast enough. I mean, your CPU time was low, but you didn't get a good travel path, so don't like it. So it seems so promising though, right? Like we're so close. Can we fix this? What do you think? So we can fix this, right? Otherwise I would not have created all these slides because it would have been a long circular thing with no resolution. So I would not knowingly have done that. It's not a complicated fix. So maybe you could, I'm not going to prove that this works, right? In 345, you'll actually do proofs of why is this safe, but it's kind of intuitive what we have to do. So I'll give you maybe a few seconds to think about that. Think about, is there anything you could change, which is not very complicated, we're not talking about changing things in a big way, that can fix this problem of sometimes, they might not be the most common times, but sometimes we might get a suboptimal path with what we've done. Anybody want to take a shot at it? I can see some teams look like they're getting close. They're very close to wanting to take a shot at it. And I'll give you a hint. I mean, what went wrong? So I predicted that I was going to drive at 60 kilometers an hour, and I was wrong, right? Actually, one of my solutions, I could drive at 100 kilometers an hour. That is the root of what my problem was. So, okay, so with C06, what do you think?
Could you check the street segment speed for the road that's after that node?
You could do like a look ahead, right? So you could look one step ahead, but it won't really solve our problem because I can just make a longer example where like you're kind of saying, look one level ahead before you make your prediction. You could do that, but if I start drawing cases where the incorrect answer comes 2 nodes later, I'll break that. And if you say, oh, look 2 nodes ahead, I'll make one with 3 nodes. And I win, right? No matter how many nodes you look ahead, I'm going to just make one more. So that won't fix it. Any other thoughts? Okay, so the root of our problem is that we're not optimistic enough, actually. So what we want in an astar algorithm is we still want to guarantee the best path, even if it costs us some extra CPU time, okay? So to guarantee the best path, what it means is I should never underpredict how much travel time, well, basically I should never overpredict. Sorry, my heuristic must always be accurate or underpredict. So my guess of how much travel time I'm going to have to get to the destination always has to be either correct or an underprediction, okay? It can never overpredict. The reason it's not okay to overpredict is basically this node. By overpredicting how long it would take to get to the destination, I concluded that it was for sure inferior to this solution that I was looking at already, and I never looked at it, okay? If that can never happen, then any solution that might be better than the ones I'm currently pursuing will be looked at eventually. Does that make sense? So that's, if you think about it, it's kind of logical. And this is actually how you can see Dijkstra's is really a special case of astar. If I actually assume that the travel time remaining is 0, it's like the most optimistic heuristic I could use, that actually gives me Dijkstra's algorithm. I just sort on the known time, the best time to a node. But I can use heuristics that are better than that, but still never overpredict. And the never overpredict's really important. Again, what that does is it guarantees that any solution that's in my wavefront, any partial solution that could possibly beat the solution I get to the destination by following some other path will be looked at. Okay, so I'll never get all the way to the destination without looking at other things that have any chance of beating it. Okay, so I gave you a big hint there. I must not overpredict. So we're predicting travel time from a certain node to the destination. How could I not overpredict? I mean, I could just predict 0, all right? But that gives me Dijkstra's algorithm. So it'll work, but I won't get any of the CPU benefits of an astar algorithm. So what else could I do? My goal is to basically not be as conservative as just predicting 0, but never overpredict. So I'm going to go to C06. Yeah?
Could you set the speed to the highest in the map?
Yeah, so you can, in load map, you could go through the whole city. You could find the highest speed limit anywhere. If you use that and use a distance that is basically as the crow flies, you'll never beat that, right? Like you're never going to find something that's faster than the fastest freeway in Toronto going exactly where you want to go. If you keep searching for that, you will not find it, okay? So that's exactly right. So what we want to do is change to, in Toronto, we could use 100 kilometers an hour. So if we used 100 kilometers an hour, let's actually just see what happens here. So I'm going to walk through this one. I would start off, let's look at my wavefront. So my wavefront initially has these two nodes on it. So I've got N2, and it's got a travel time of 45 plus, now it's 1 kilometer divided by, well, how long does that take at 100 kilometers an hour? And 1 kilometer at 100 kilometers per hour is, I think, 36 seconds. Okay? So that is equal to, let's see, 81 seconds. Okay, and N1 is 30 seconds plus 1.5 kilometers at 100 kilometers per hour, which is 54 seconds. That one I already did. So that's equal to 84 seconds. Okay, so there's my wavefront with this new sorting. I'm going to look at N2 again. It's at the top of my wavefront, and I know what I'm going to get. We already showed it. We're going to get N3, and N3 is going to have a travel time of 75 seconds, because if I go back one, I showed that I had a street segment of 30-second delay, and I'll have 0.5 kilometers left. Okay, so I take off my N2. Now let's look at this N3. So it's 75 plus 18 seconds. That's the remaining estimated time to get to the destination. This is half a kilometer divided by 100 kilometers an hour. And that is, let's see, 83, that's 93 seconds, okay? So N3 actually looks worse now than N1. So I go and look at N1, and N1, we already said, basically goes straight to the destination and reaches it in 96 seconds. Okay, so we'd find it. Because we were using an underestimate, we basically didn't drive as directly towards the target. Anything that possibly could be better, we would look at before we got to the destination, so we found this better path. Okay, so does that make sense? So that is how you develop the astar heuristic for a street map. Okay, so let's talk about implementation a bit. So we're changing the wavefront sorting. We are not changing this best time. So I kept referring to this variable best time. Remember we had a node array where we stored the best time we found to every node so far? You need that to be accurate. So a common problem students have when they make an astar algorithm is they get this sorting function based on total estimated time, and they start getting confused about what do I use it for. You're just using that to sort the wavefront. It's just ranking promising solutions. The time to a node must be accurate because you are saying what's the best way I ever got to this node, so you use only your known best time, like the time behind you from the source. Your wavefront's going to get a little bit more complicated. Okay, so we already had, what's the node ID, what's the edge ID that I used to get here. We already had this travel time, like what's the best time to get to this node or what's the total time to get to this node so far. And now we're going to have another number that we actually sort on. And that could be anything, but you saw a good one would be total estimated time using the techniques that we just went over, okay? So that's, any questions on astar? Okay, so that's good. Let me do a quick demo of this. Okay, let's see. Okay, so let's go to Dijkstra's algorithm. Okay, so you see Dijkstra's algorithm is pretty good, right? So I do just like watching the animations of these things, right? So this is what I do in my office when I get bored. But you see Dijkstra's explores outwards in kind of like a circle, right? It explores outwards in all directions. It's not a perfect circle because it's actually exploring outwards in sort of travel time to this node. So you see it follows the highways a bit more. When I turn on astar, it's going to look a little bit different. Let's see. So you see, if you watch that carefully, you'll see A star goes more towards the destination. It doesn't explore as much in the wrong direction. Whoops. So it makes it faster. It doesn't make it massively faster, okay? A star is actually also order n log n. That's what Dijkstra's is, but the constant's lower. A star typically is around 3 times faster in a city map. So it's worth doing. It's not much additional code, but it's not like 100 times faster. It basically just is more targeted at going towards the right direction, maybe 3 times faster. Okay. Okay, so no questions on that. I'm going to go into a few tips on how you tune for performance and correctness here. Okay, so milestone 3, how many people have started on milestone 3? Okay, a few, good. All right, so don't leave it to the last day. I mean, you still have time, but I wouldn't leave it to the last 2 days because it's going to be stressful. You're going to find when you look at milestone 3 that there are a lot of tests. And you go, well, where do I start? We built you a lot of tests to actually help you. So the first set of tests, you'll see have this path cost in their name. Okay, so there are a few of them for a few different cities. Path cost is a really simple function. It's just making sure you can compute the time taken by a sequence of street segments, including the turns they imply, correctly. Because if you don't have that specification right, you're never going to write a proper pathfinding algorithm. So this is not very hard to write. It's not worth very many marks, but make sure you get that right first. Then we have some tests that have simple legality in their name. Okay? Simple legality are short paths. Okay, some of them are like one intersection right beside another. Some of them are one intersection, like you're 2 intersections away. So these are tests that are easier to debug because your algorithm's not going to run for very long, right? The target is either right beside you or maybe 2 intersections away. One of the challenges you'll find, the amount of code you have to write for the M3 algorithm is not that much, but it has to be correct. And if you get it wrong, it's hard to debug because there's so much data flying around. Right? Some bugs where you just do some problem in how you sort your wavefront, for example, can result in incorrect answers, but because you just searched through 50,000 intersections, it can be hard to figure out what did you do wrong. So these simple legality tests are intended to make that easier, right? The target's right beside you. So debug those. And for simple legality, we're just checking you get a legal path. We don't care how good it is. Then we have legality tests. Okay, legality tests now, some of these paths can be long. They can go all the way across the city. They might go through, 100 street segments. And again, we're just checking that they're legal. So we're seeing, can your algorithm actually find those paths? Then we have tests called simple optimality. Okay, so optimality checks not just that you have a legal path, but that it is actually the shortest path. It has the lowest travel time, or sometimes there can be several paths that are very close. We'll accept any of those. So all our tests are written to have a tolerance. So there isn't like one path you have to match. You just have to find a legal path that is close enough to the lowest travel time that we found. And the simple optimality, again, are to make it easier to debug. These are like intersections that are very close together. So if you have a problem, you look at those ones first. Okay, then we have optimality. So the optimality ones now can go all the way across the city, but again, you got to get a fast path. It's not enough just to have it legal. And finally, there are performance tests. And the performance tests start at medium, then go to hard, then go to very hard. The very hard is not actually that hard, okay? So maybe that's a more intimidating, what you've learned in lecture, you will pass the very hard tests, okay? So, but you will, given the name, you will now feel really good about yourself when you do that. So once you get the optimality working, you start paying attention to the performance tests. And if you wrote Dijkstra's algorithm, you should pass the vast majority of these. If you get all the way to A*, you should pass them all, okay, with like a reasonable implementation. We also give you, a smaller city. Interlaken is like a town of like 7,000 people. So that's also easier to debug on, right? It's not such a big thing. Okay, so I just mentioned this already, but basically debugging algorithms is tricky because it's not just that your code doesn't crash and does approximately the right thing, it has to do exactly the right thing. So it's best to start with very simple test cases. So that's those simple tests. Intersections that are right beside each other. You if you have any problems in your algorithm, and it's likely you will, you want to watch it in the debugger, right? And you watch it in these simple test cases to see, is this doing exactly what it should? If it doesn't exactly, put things in the priority queue with the right sorting function and so on, then it's not going to be right. So walk through it in the debugger, see that it's doing the right thing. Okay, so you try a slightly harder case. So some of the cases in simple are just, as I showed here, intersections that are right beside each other. If you pass all those, the next set in that same test suite are a little harder. They're like 2 intersections apart. So see if that works. Okay? And then we get into the more general ones that I told you about, where you can go all the way across the city. We give you, some of the tests are run with a turn penalty of 0. Some are run with a turn penalty of some other number, like 15 seconds. That's done on purpose. Of turn penalty 0 kind of deactivates some of your code. If you pass all the turn penalty 0 cases, but you fail the ones where turn penalty is non-zero, well, you know where to look. Okay, so this is part of kind of creating good unit tests. We create unit tests that will help you debug, because you see what's the most complicated thing I pass, and then what is the next thing that was added in where I start to fail. Start looking at that part of the code to debug. Okay, so then the most complicated tests for legality and optimality are far apart, turn penalty is not equal to 0. Dijkstra's algorithm and astar algorithms with this turn penalty are actually not guaranteed optimal, but they'll be close. Okay, so with no turn penalty, they will get the perfect answer. Turn penalty makes things a little harder, and unless you go one step further in algorithms, which we don't expect you to do, you'll get answers that are slightly suboptimal, which is fine. Our solution accepts those. Okay, so don't worry about that. So run valgrind if things are looking weird, or I just run it once in a while. I want to know when I'm testing a program that there are no memory faults. So run that. And the debug check build is also useful. So it checks for out-of-bounds memory accesses, just like valgrind, but it checks some additional things. It actually checks, well, that you're not going outside the range of STL containers like a vector. You're going to wind up using, almost certainly, a priority queue or a heap that comes from STL, because there's no real reason to write your own. You just ask for theirs. One of the things the debug check build does is it actually confirms that the priority queue is actually still a heap, because there are bugs you can put in your code where you break that. If you're doing certain things with pointers, you can actually break your priority queue. The debug check build will actually catch that. So there's some additional checking it does. So I guess these are just useful tools. Run valgrind, run the debug check build once in a while on a small test case, because they will be slow, to make sure they don't flag anything. Just makes you more productive. Okay, that's the correctness. Then you got to tune for speed. So tuning for speed, the biggest hammer you have is the algorithm, right? If you use the wrong algorithm, you'll be much slower. Then data structures. If you use very inefficient data structures, it'll be slower. And then last, low-level code. Low-level code is like thinking carefully about how many if statements and so on. We don't expect you really to tune low-level code. The way we set the speed tests in this milestone and all the other ones is we basically take our reference solution, which is reasonable, but we haven't micro-tuned it, and then we multiply by some number, okay? So typically 2.5 times. So you don't have to micro-tune your code. So sometimes students, they want to go tune their low-level code first, and it's the least powerful technique. Start with the algorithm, then the data structures, and then this last one only if you need it. It's hard to, when you get to these bigger test cases where you're going far across the chip, it's hard to see what's going on just in the debugger. The debugger is good for watching carefully, did I do this loop properly, et cetera, but if you've got things that only show up when you go through, they're algorithmic flaws that are more visible on big test cases, it's hard to see that in the debugger. So graphics are very helpful here. I showed you, we visualize how our algorithm is working, and we can see what is it exploring, and that can be useful. So I'm going to show you a little bit of code that you can use to visualize what your algorithm's doing. In your final submission, you should make sure this isn't on by default, right? You should have like an if-def or a control variable. We actually turn your graphics off when we run the M3 tests, so it would probably be okay anyway, but we have seen students manage to turn graphics on in ways we didn't expect, so it's best to just turn off the visualization before you submit, even though we probably will be okay and turn it off ourselves too. Don't test us. The reason you don't want that is you don't want to slow down your algorithm with a whole bunch of drawing when we're testing it, okay? So we do try to turn it off, but if you changed EasyGL in a funny way, we might not be able to turn it off. Okay, this code I'm not going to go through in detail, but basically you can just take this code and use it to visualize if you want. So I put an if-def around it, so if I don't define visualize, the code just gets ripped out, so it's not going to slow my algorithm down at all. But if I do have this define visualize line in and it's not commented out, this code will be active. And I basically just said, give me the renderer. And I've got a routine that draws a street segment. So I say draw this particular street segment that I'm exploring right now. This is animation. Okay, we're not going to like basically wait for user input, so we have to call flush drawing. And flush drawing will basically make it draw right away, okay? Otherwise, you won't see this animation draw nicely. It'll wait. And generally, it'll draw so fast you can't see it. So we're using the chrono library to delay, and that's basically the code shown down here. I just basically get a time. So I'm asking for a time of 10 milliseconds. And then basically, I call a function called sleep for, which basically says don't do anything for this amount of time. So my program actually goes to sleep for 10 milliseconds. And I could change this number if I want the animation to be faster, or I leave it at this if I want it to be slower. So it's not very much code, right? Code like this will visualize your algorithm. Okay, another way you can speed up your program that's not fast enough is you can use what we talked about in tutorial 7, and we also have a quick start guide on it. So you can profile. You can see where is my time going? Is there some routine that's getting me? But first you want to think about whether your algorithm's doing the right thing, because this isn't going to really help you find problems in your algorithm. This is just going to help you find problems in your low-level code. Okay. This is from our actual solution. So it shows my turn computations took some time, took me some time to figure out what's connected to this node, and it took me some time to manage the priority queue. None of that looks crazy, right? All of those things I think should be in my inner loop, so that looks reasonable. As I mentioned in tutorial 7, you can profile with either the release build or the profile build. And there's a trade-off here. The release build is what you actually are going to get run on submission. It's got all the optimizations on. Profile build is the same, except we turn off one optimization called function inlining, which can basically paste the body of one function, a short function, into the caller. That makes your program faster, but it does mean your profiling information is less detailed, because some of your functions have kind of been stuck inside of each other and you won't get information on them. So both of these builds are useful. I usually start by profiling the profile build, because at least I'll see all my functions. It'll be a little bit distorted, because it probably ran 30% slower, but I see everything. It's easier to interpret. Any questions on that? That's it for milestone 3. Okay, so I'm going to quickly, hopefully, inspire you that fast path search is important. So one of my research areas is design of integrated circuits and CAD tools for them. So somebody mentioned this earlier on, but one of the places you use fast path searches is in FPGA CAD tools, like Quartus. So in Quartus is something one level beyond an astar algorithm is one of the algorithms that's inside Quartus, which you used in 241. So this is a recent Intel FPGA. It's called Stratix 10. It has 43 billion transistors, which together form 10 million logic elements, right? And a logic element can implement a few gates. We need to connect all those logic elements together. Each of them has several inputs. So you got about 40 million signal paths to connect. And you do that in a graph that represents all the little bits of wiring and switches in this chip, which is a graph with about 300 million nodes. So it's actually much bigger than, Tokyo has about 1 million nodes, okay? So this is 300 times more complicated than Tokyo. And you're not trying to find, one path, you're trying to find about 40 million paths. So next time you say Quartus is slow, you should say Quartus is pretty fast given what it's doing, right? So, okay, we also want these paths to be good. To make your circuit fast, we want them to be shortest paths, because that actually corresponds to less delay, and we can clock the circuit faster. These paths can't overlap, because that means that it's an electrical short. So there's actually some more than just shortest path on here. Shortest path is a key building block, but we have to have congestion resolution algorithms on top of that. the algorithm that is the core that's connecting all these things together is one level beyond astar called a directed search. What a directed search is we give up on finding optimal paths, like that we can guarantee this is the shortest path, and we actually, that heuristic where I said it must be a lower bound, it doesn't have to be a lower bound anymore. It can just be a good guess. That means that we can't guarantee we get the best answer anymore, but there's so many interacting algorithms here, we couldn't really guarantee that anyway, and it makes it faster, okay? But the amount of code change from astar is small. It's all cleverness. Chips go even bigger now. Okay, so Cerebras is a startup that has a big office here in Toronto. Lots of my former students are there now. They take an entire semiconductor wafer and make a machine learning training system out of it. This wafer has 2.6 trillion transistors in it. And they use those to make 850,000 processor cores. Okay, so your laptop might be 2-core or 4-core or maybe even 8-core. Okay, this is like an 850,000 core system. And they need to connect all these cores together. They have to exchange data. They have something called a network on chip. It's like a baby internet inside there, and they use shortest path algorithms. Again, has to be really fast to connect it all together and make all the processors exchange data properly. So yeah, there's lots of applications for really fast graph search. Okay, and in the last 3 minutes, I'm going to talk about something completely different. So, programming languages. So in this course, you're learning C++. And I often have students ask, how important is C++? Should I be learning Python? Should I be learning JavaScript? My great-grandpa told me that the future is Rust, right? Is my great-grandpa right? Etc. So this is from 2023. Spectrum, every year, does a survey using job postings, projects, etc. What are the most important programming languages? And Python actually came out on top, so it is an important language. It's a good one to learn. You will almost certainly learn it in 3rd and 4th year if you haven't already. And then C++ is 4th, which is pretty good, an important language. But the other thing I want you to recognize is Java, C++, C, and C# are all derived from C. And C#, C++, and Java are all basically very closely related ideas of how to add object-oriented programming to C, okay? Java's original name was actually C++... It was basically, we will make C++, but take some features out to be a little less complicated. So that was actually one of its key goals. And C# is Microsoft's language of, we are not going to license Java from Sun Microsystems, one of our competitors, so we are going to make something else, which we will not call Java, but is a lot like Java. So all 4 of these are actually very similar. From your knowledge of C++, you can actually code any of those without too much training. Python is different and serves a lower performance but get my program working faster niche. And then in front-end web development, the most important language is JavaScript. It's kind of a horrible language, but it's gotten gradually cleaned up, so it's widely used. And there's another variant of it called TypeScript that does type checking. So these 2 really are not different languages either. They're related to each other. So anyway, why did I show you this? You're learning one of the most important languages, and you're also more importantly learning one of the big classes of language, like the C++, Java, C# group. You should and will learn